Let's take a look at some important implications of what we've seen in terms of relative motion of conductors and the electric field generated by dB/dt, and what that meant to Einstein. After that, we'll talk about self-inductance, which is an important concept for a lot of circuits. You've probably noticed that there's a similarity between the generation of an EMF by the motion of conducting loops through a B field, where the flux, which is enclosed by the loop, changes with time, versus having fixed loops where there's a changing flux inside the loop. So we have a dB/dt, for example, unequal to 0. The first, if you remember correctly, is a result of looking at the force on charge in the conductor. And so we have the Lorentz force V cross B, which is causing separation of charge, which is equivalent to an EMF. The second arises from applying the Maxwell's equation for the curl of E. That relates the E field that's generated to this change in B, which is the change in flux. What I just said is that's Maxwell's equations, which actually was derived from Faraday's law. If all you could measure was the EMF, you could really not tell the difference. And so, for example, if you have a loop behind a wall, which you can't see what's happening over here, things are happening over here, and you see an EMF between the wires. Because of the fact that both of these techniques or situations give you an EMF, you can't tell them apart. This is a situation where you have two different phenomena being equivalent. And so that led Einstein conclude that examples of this sort, together with the unsuccessful attempts to discover any motion of the Earth relative to the light medium, this was the search for ether, suggested that the phenomena of electrodynamics as well as mechanics possess no properties corresponding to the idea of absolute rest. This was an important thing, and so what we're really talking about is the foundations of special relativity. So I wanted you to see what we were studying actually had a big impact on the development of relativity. Let's look at self-inductance. We have emphasized how two systems, let's say A and B, interact where we have time-dependent changes occurring in A. So these could be currents that depend on time, motion of conductors with inhomogeneous B fields. And the consequence is that it induces currents or EMFs or E fields at or in B. And obviously these systems could be overlapping. If we consider now a single system, so we're not going to have two systems but simply one, where we take a loop that has a resistance R, where we're going to change the current with respect to time by, say, varying a voltage source with respect to time. We'll call that V of t. And for simplicity, we'll take the case where V is increasing with time, and so therefore the current is increasing with time. So what I'm talking about is a source of potential which changes with time, causing a current in this loop to change with time. This will generate a flux change through this enclosed surface. This generates an EMF in the loop that tries to oppose this change in itself. In other words, the buildup of flux in this loop. So here I've shown the potential increasing in the direction I show here, so current will flow in this direction here, and by the right-hand rule, this surface will be penetrated by a flux symbolized by these red arrows. If we now look at the effect of the induced effects, so the induced EMFs, it's going to be easier to think of an I-induced, realizing that it's not real, that will flow to produce an imposing flux. And so in this case here, because flux is building up with time, remember we said that V was changing positively with time, so this flux is growing, we have to counter it with this flux here. Well, if you had a current flowing in this direction, opposite to the I of t, the right-hand rule would give you a flux in this direction here. This helps us pick the direction of the opposed EMF, and so it'll be consistent with this I-induced. We'd have plus to minus for the I-induced, and so therefore we put these signs on the EMF induced. this current, this I induced, is in the opposite direction to I of t, and so the EMF induced has the opposite polarity of V of t. And this is only because we're increasing V with time. And that helps us pick the direction of the EMF and therefore generate the I induced. I've tried to show that symbolically in the figure, and in this case here, because the EMF is opposing V of t, we call it a back EMF. So we can take these circuit elements and lump them. So we're going to take the EMF, I had already shown it as a localized EMF, and we'll separate it from the voltage source and the resistance. So we end up with an equivalent circuit that looks like this. So here's our changing voltage. Here's our resistor, so that's as is, and then we have the separated EMF over here. If we have this increasing with time, therefore we have a positive di dt, then the polarity of EMF is shown either here or here, and it looks like a time-dependent battery opposing V of t. So notice all I've done is translated this over into this part of the circuit. You can see better that this EMF is opposing this one if this is increasing with time. Now don't forget that if this changes direction, this is going to flip also. So we've got then this reduced EMF, which is going to therefore have a reduced current through the resistor. The basic idea then is that you have a potential, which is the difference of these two quantities here, reduced so that you get less current through the resistor. And don't forget, for an increasing I of t, EMF sub t must oppose this change in V. So we write this EMF induced as equal to the change in flux with respect to time, and the minus sign is our Lenz's law reminder. We can separate this out by differentiating phi with respect to I, and then I with respect to time. If we do that, then we can use the following relation. We put in V of t is equal to EMF induced plus IT of R, and basically what we're doing is just simply taking this equation and setting it equal to I times R, because the potentials will be the same across those two terminals. If we have then the signs that I show here, those are for illustration only because it'll depend on what the actual time dependence of the voltage. But what I show here is for the increasing V. Suppose we have a potential which is a function such that at 0 time the V is equal to 0 and it's increasing with time. That gives us the signs that we show here. So I've said this about 100 times now. The minus sign says choose the real sign so that this EMF fights the change caused by di dt. I think you're getting it by now. We're going to now introduce self-inductance. So we've written EMF just like we did before. We're going to let all of this flux occur in a single circuit element. And we are going to represent that by a solenoid. For most elements where we have this isolated magnetic field changing with time, this quantity here, which we had written up here in terms of the change in flux with respect to time, for most situations that we're interested in, this is a constant, and we call it L. And L is the element's inductance. Rewriting then our EMF induced as a function of time, it's equal to L times di dt, where the sign is used to get the right direction of the induced flux change. So if you look at the circuit that we've had here, we've replaced the EMF as a function of time with L times di dt. In order to get the EMF, it's going to be L times di dt. Okay, so right up here, here's the EMF induced is equal to L di dt with the correct sign. Rewriting the potential, so we have the potential that we're driving all of this with. Here's the potential that's dropped across the inductor, and here's the potential dropped across the resistor. So if we look again, here's our voltage source, the real one. We've got this L di dt plus I times R. And I just want to emphasize that for this increasing, we know that this is increasing. So this term is plus, this term is plus, and this term is plus because of the direction of the current, which is right through here. So that'll give us a plus potential. Let's go through this again. Here's our potential. This is going plus with respect to this terminal here. Current is going to flow here. This part of the resistor is exactly this potential, so we put a plus here. The potential drops as we go through the resistor, and then because of the EMF opposing this potential, we have a plus and a minus. Now realize this is at the same potential, but the change going from here to here is from plus to minus. And then we come back to the minus terminal here. If you wanted to, you could do what we did before. We could lump these two terms here into one potential, and so this would be the potential that's across the resistor, and so that'll give us I times R. And that minus sign tells us that if this is a plus change, it's going to reduce the overall potential. Let's take a look at some simple voltage versus time equations. So I'm just going to take this as a constant times t to the n, and n is an integer, and we're just going to look at two cases, n equals 1 and n equals 2, and so we'll use Mathematica. Given that, here's a program, and here's the same equation that we had before, and what we're going to do is solve the differential equation. So here's the equation right here, same equation. We're going to assume that the current is 0 at time equals 0, so that's the condition here. And by the way, the double I is simply because Mathematica treats the I as the imaginary I. If you put in double I, it treats it as a variable. So this is going to be solving for the current with respect to time, and the variable is time. In order to plot, we have to put in some values. I'll let k equal 1, r equal 1, and I'll just take l equal 5, just for an example. Here's the linear voltage with time. Here's the quadratic with respect to time. So we'll plot both of these. What I'm going to do here is just run this. Here's the solution for the current for the linear case. And that can be simplified, so that's right here. It has a factor here in terms of the L dependence with an exponent which decays with R over L times T. You remember that if you have T over tau, tau is the time constant for this function decaying. L over R is an effective time constant. We take this and plot it as a function of time, and this is the current with the inductor. Here I've let the inductor disappear. So this is just the current through the resistor as a function of time linearly. So as you expect, you get a straight line. But here's what I want you to see. This difference here is the actual difference in the current due to the inductor. So the inductor slows down the current from what you would get if you didn't have the inductor. Okay, so now let's look at the second case. It's more complicated. You could probably simplify this some. But nonetheless, this equation here is the current, I of t, just as we got before, except it's a more complicated function because we have v of t going as t squared. So here's the response right here. This is the current through the resistor if there was no inductance, and this is the curve if you had inductance, and again it slows everything down. It's fighting the increase of flux, and so therefore you get this response here. I don't know if this is helpful or not, but here's the current through the resistor with no inductance, linear. Here's the quadratic, resistance only. This is the response, it's this blue curve here, for the current with the inductor, t squared, and then the v of t. You say, well, gee, that's interesting, but what happens if you change some parameters? Well, let's just change the inductance. So let's go to 25 here and 25 here to get the same result. Run that, and you can see that the difference between the current without the inductance and with the inductance is significantly more because we've added more inductance. And the same goes for the quadratic term here. This is a bigger change, a slower response from the response with resistance only. So let's actually calculate the self-inductance of a simple case. Before we do that, I just want to tell you about the units. The unit of L is the Henry, and 1 Henry, if you go through our equations, will be 1 Tesla meter squared per amp. That mess we call a Henry. So what we're really talking about then, this is the inductance, And so if you look at the differential of B dot A with respect to current, so you've got Tesla here, you have meters squared here, and then an ampere down here. So that's where you get these units here, and that's a Henry. In the laboratory, these are quite a bit smaller than 1, so you typically have micro and millihenry magnitudes for the inductance. So let's take the case of a finite solenoid. It's going to have turns represented here, and it's going to have a cross-sectional area right here. We're going to assume that the flux phi passing through the solenoid is just given by a constant B. So this would be like if it were very long, but we'll just take that. So here's the total number of turns. Here's the flux, B times A, multiplied by the number of turns. And the B that we'll take is the B that's equivalent to an infinitely long solenoid. So N, remember, is the number of turns per unit length. So if we rewrite that then, here's phi in terms of the current. Right away we're in good shape, because when we differentiate this with respect to I, this will disappear. We'll be left with just factors that we can measure. Remember that N will be equal to N times the length. Little l is the length of the solenoid. Putting that in, we have phi equaling this quantity here. We regroup, and so we're left with this factor here in front of the I coil. So this right here is going to be the inductance, because when we differentiate with respect to I, then we get these factors here. These are simply geometric properties of the coil, and how tightly we wound it, and the length of it, and the area. The inductance, in a sense, is like the capacitance. If you remember, the capacitance is only dependent upon the geometry of the plates that make the capacitor. Here, it's a function of the coils of the wire that make up the inductor. So just for fun, let's take some numbers. So we'll take N 50 turns per centimeter. Let's take a diameter of 5 centimeters and a length of 20 centimeters and find out what L is. We have to convert that to meters, so we'll have N equaling 50 times 100. We'll have D 0.05 and L equal to 0.2. The area is pi d squared over 4, so you put in the diameter, multiply by pi over 4, square the diameter, and you come up with this quantity here. In meters, of course, it's a pretty small number. So then we go to our equation for L. Here's our mu 0, here's our little n squared, here's our L, here's our, oops, made a mistake, this shouldn't be here. This is just a typo. So if you put in the area here, you'll end up with L equals 12.3 millihenries. So now let's look at the L of a toroidal coil. So we have a toroid with a rectangular cross-section which has an inner radius A, outer radius B, and a height h. And it has a total of capital N turns. So find L. Well, for that we need the flux inside of the toroid, and so we need B. And fortunately, this is a slide from one of the earlier talks. We know the B field inside. This was the derivation, all of this. To find the B, we use Ampere's law. And so inside the toroid, we end up with mu 0 times the current times the number of turns divided by 2 pi r, where r is the position between the coils where you want to know B. So it actually changes with the position inside. Let's determine the cross-sectional area. And so if we take B minus A is the width of the toroid times h, that will give us the area through which the flux flows. Now what I'm going to do is take some average values. So we're going to take the value of R to give us the average B, and the average value of R will just be halfway between A and B, so this would be B plus A divided by 2. We can approximate the flux inside the windings by just taking that average value times A, and A is this quantity up here. We have mu 0, this is just going into the toroid equation, mu 0 I times capital N, 2 pi times R average, B minus A times H. So I've just used the equation on the previous slide. if you take that result and differentiate it with respect to I, you'll notice that again you just have a linear dependence on I, and you're reduced to parameters that only depend on the geometry of the coil and mu 0, and of course the number of turns. So that's a pretty simple answer, and it would be useful. But if you look at what Faraday would say, okay, this above approximation made Faraday roll over in his grave, because we can integrate the flux that we had from the B that was exact. And so we can integrate over the cross-section to get a more exact answer. So if this is the center of the toroid, and the distance to an element of area, which is ds times h, if that parameter is s, then the B field, remember, just depends on 1 over r across this cross-section. So if we take the flux through one turn, it would be B dot dA, and we take the area element that I showed here, and so here's our h, and here's our ds, and we take our B dependence on s, which is 1 over s. So all the constants come out, and we're just left with 1 over s ds, and we integrate from the inner radius to the outer radius. So when you do that, you get the logarithmic dependence on those two parameters. Here's the total flux then. We just multiply by n. You can differentiate it with respect to I, or just drop the I, and this quantity right here will be L. So the more exact equation for the inductance of the toroidal coil is given by this, which has this logarithmic B over A. So you might want to put in some typical values and check the difference between this one and the more approximate one that we derived earlier. So next time I'd like to talk about mutual inductance, which will involve two circuits, and look at the energy that's contained in B fields.